IMMI versus the stunning 150 billion pixel diameter 1 billion star mosaic image of our galaxy by Ronald Stewart. Copyright 2014, all rights reserved. This is a comparison of the 150 billion pixel diameter 1 billion star image and mosaic and IMMI to see where it goes to and where IMMI goes to as well. Copyright Ronald Stewart 2013 to 2014, all rights reserved. Here at this URL, it allows you to use this mosaic and go into it and be able to get hands-on experience. Researchers have stitched together a picture of our Milky Way galaxy, and this result is a stunning image containing more than 1 billion stars. The picture took over 10 years to create, and it combines data from the UKIDS GPS Sky Survey acquired by the UK Infrared Telescope in Hawaii and images obtained with the VV survey data acquired by the Vista Telescope in Chile. This would present this image to the world to be the largest image in the world. The work was presented at the UK National Astronomy meeting by Dr. Nick Cross from the University of Edinburgh. However, when looking at the first image, it's concentrated down into an area of computer screen which only measures 1/2 inch in height by 6 inches in diameter, which is staggering. There's a small box in the right top corner that has a plus and negative symbol for enlarging or decreasing the mosaic image zoom capability, and how deep or not you decide to go inside the mosaic image. There's also a left to right pair of symbols for moving either to the left or right within the mosaic image as well. What we'll be doing here is going down into the image like anyone else and get hands-on experience, and then show where this mosaic stops with 10 years of research, and then where the IMMI technology then begins. Now we begin to zoom in to the mosaic here, which is 1 billion stars, and the purpose and object here is to go into this small square that we see here where the arrow is pointing to, and the first area that we'll be going into will be where the little tiny dot is, where the yellow arrow points to. Our final goal will be toward where the aqua arrow points to, which is so small at this point right now in this video it cannot be seen. But what we'll do next is take a look, and the goal is to take a look at stars that are called neutron stars. And inside these neutron stars, we will see what their accretion is and exactly what may or may not be happening. Here is the general area that we'll be zooming down into and be taking a look at more as to what is or is not the case in this investigation into this 150 billion star, 150 billion pixel diameter, 1 billion star mosaic. We continue to zoom in. We continue to get closer and closer and closer. The mosaic, and here is now where the arrow points to. IMMI is going to start going deeper and further into outer space and show all the things you are getting ready to see as we continue to now enlarge the first area of investigation. The neutron star is a transitional transformation and is our first investigational study, where the arrow points now as we see it getting larger and larger and larger as we investigate more and more. Which we see now in the middle where the yellow arrow points to again, and the other arrow makes a circle around it and shows what we'll be looking at as far as the star is concerned. Neutron stars have the capability of having a high magnetic content on the inside of the star. But yet, there's also other characteristics and features. Now, where the blue arrow is there, where it's pointing to, is our final destination. But neutron stars have either a blue to bluish green center, and this is what we're going to be seeing here to the image. Here again, we can see much closer the star, but we're going to see it enhance it even more. And what we're going to take a look at here is exactly what is going to happen. We get higher and higher enhancement of this neutron star. We're actually getting closer and closer inside of it. Now here is maximum enhancement of this star. Again, where it was before, maximum enhancement. Where it was before, maximum enhancement again. So here we can see the center very clearly, and we can see the type of radiation around the star itself. Yet we also see the blue, and we see what almost looks like a hole in the center, which it is not likely to be a black hole. It is really just a magnetic center that has other properties as well. Now first we're going to go to that first star here where that area is going around. It'll be the second area of location we'll investigate. We'll next investigate this third area here, and the last area that we'll investigate will be approximately right there in that area. It is too small to see at this time, and that little star right there that we just pointed to is where we go to again as we get closer and closer. Now we're beginning to leave the first star, and we're going to be able to go back and take a look at the final one there in our destination. But the next area that we'll be investigating, as we zoom in toward it, we see the yellow arrow is getting closer and closer to us. Right there where the yellow arrow points to. We're going to go right down the throat of this star right here. Now we see that something's happening to the star on the left and the neutron star, which is possibly neutron star on the right. Here at this URL, this is a NASA image, and credit goes here to NASA. This is an artist's rendering of what they think a neutron star looks like. And it's an artist's rendition of a magnetized neutron star which has a blue object in the center, accreting material from a binary companion large red star, in which they have satellites to measure this. But this is the first time that imaging evidence on not only the large one that we see in the upper top right corner where the accretion is happening between two stars, but also in the bottom right corner as well. This would be a neutron binary system. Some neutron stars are found in binary systems with other stars, and this is what might be happening here. If the star's orbits are close enough, material from the larger donor star may accrete into the neutron star. This accretion process can produce large variable outbursts of X-rays, and the new star satellites are able to observe this. In some neutron star binaries, quantum mechanical effects cause light at specific energies to scatter away from the line of light and also the line of sight. This phenomenon is called cyclotron resonance scattering, which produce dips in the X-ray spectrum and can be measured. By measuring the energies at which these dips occur, the new star satellites directly measure the strength of this magnetic field of these neutron stars and study the accretion process. And here, what the IMMI process is showing, that there is a accretion process going on between the large star and the smaller one to the left. And accretion is where the energy transfer is going from one star to the other one. Now, as this happens, it also allows a high magnetic resonance to take place in the center of the neutron star, which we will be seeing here, which could be going through also, which the imaging evidence supports not only what the new star satellite is showing, but also we're going to go right down the throat and show that there may be what we may be able to see as we now zoom into the star itself and down its throat. It's turning different radiation colors. We're going to be able to see that there may be high magnetite gases inside this star, which is causing it to have a very high density and accretion magnetic gaseous process. We zoom in closer and closer to the inside, and we see this taking place in these gaseous conditions. Here, in what now is the first imaging evidence, and this has been where IMMI has gone further than the 150 billion pixel diameter image